Space has rules, laws of physics, mathematical constants, predictable patterns that scientists have spent centuries mapping out. We thought we had it mostly figured out. And then space just laughed at us. Because scattered across the universe are things that shouldn't be there. Objects that break the rules, phenomena that make physicists stare at their whiteboards and question everything they know. These aren't just weird or unusual. These are things that, by every calculation, every model, every law of physics we understand, simply should not exist. And yet here we are. Starting at number 10, we have cosmic rays that are too powerful to exist. In 1966, two physicists named Kenneth Greisen, Vadim Kuzmin, and Georgy Zatsepin figured out something important. They calculated that cosmic rays, high-energy particles flying through space, have a speed limit. When these particles travel far enough through the universe, they interact with the cosmic microwave background radiation and lose energy. It's basically cosmic friction. So there's a maximum energy level any cosmic ray can have if it's traveled a long distance. Scientists call this the GZK limit. Then, in 1991, we detected the oh my god particle. A cosmic ray so powerful it broke the theoretical speed limit entirely. It was moving at 99.99999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999% the speed of light. The energy it carried was equivalent to a baseball thrown at about 60 miles per hour, packed into a single subatomic particle. That shouldn't be possible. The GZK limit says it can't exist, but it did exist. We measured it. And to this day, nobody can fully explain where it came from or how it got that powerful. It just showed up, breaking the rules, not caring at all. At number 9, we have magnetized gas filaments stretching across the galaxy. When you look at the center of our galaxy, you'd expect gas, stars, black holes, the usual cosmic stuff. What you would not expect is enormous filaments of magnetized gas stretching hundreds of light years long, perfectly perpendicular to the galactic plane, organized in a way that looks almost deliberate. These structures are massive. Some stretch over 150 light years. They're threaded with magnetic fields far stronger than they should be given their environment. They appear in pairs and groups, evenly spaced, like someone lined them up on purpose. Scientists discovered most of these recently, and the reaction from the astronomy community was essentially, what on earth is that? Except it's not on Earth. It's at the center of the Milky Way, and nobody expected them, nobody predicted them, and nobody fully understands what's creating them or why they're so perfectly organized. Space isn't supposed to be tidy. These filaments didn't get the memo. Number 8 is the Haumea ring system, and it breaks everything we thought we knew about where rings can exist. We know Saturn has rings. Jupiter, Uranus, and Neptune have rings too. But these are all giant planets with powerful gravity fields that can capture and maintain ring systems. That makes sense. What does not make sense is a tiny, potato-shaped dwarf planet in the outer solar system having a ring system. Meet Haumea. It's smaller than our moon, shaped like a squashed football, spinning so fast that a full day on Haumea lasts only 4 hours. By all known models of how planetary rings form and survive, Haumea should not have rings. Its gravity is too weak, its shape is too irregular, its spin is too chaotic. And yet in 2017, astronomers confirmed it absolutely has a ring system. The ring shouldn't be stable. It shouldn't have formed in the first place. Every model we have says the particles in that ring should have either collapsed into a moon or drifted away into space billions of years ago. But there it sits, a neat little ring around an object that has no business having one. Haumea read the rulebook, shrugged, and did whatever it wanted. At number 7, we have neutron stars that are too massive to exist. Neutron stars are already extreme objects. They're what's left when a massive star explodes in a supernova, and all the matter collapses down into a sphere roughly 12 miles across. A teaspoon of neutron star material weighs about 1 billion tons. They're basically the universe's way of showing off. But there's a limit to how massive a neutron star can be. Beyond a certain mass, the gravitational pressure becomes so extreme that not even the quantum mechanical forces holding neutrons apart can resist it. The star should collapse further into a black hole. Physicists calculated this limit and felt confident about it. Then we found PSRJ 0952-0607. This neutron star is 2.35 times the mass of our Sun, comfortably above what our models say should be possible. At that mass, it should be a black hole. But it's not. It's spinning 707 times per second, happily defying the physics that says it shouldn't be able to exist in the state it's in. It's just sitting there, too heavy to be what it is, not caring about theoretical limits at all. Number 6 is the enormous Lyman-alpha blob, and scale alone makes it terrifying. The universe has structure. Galaxies, galaxy clusters, superclusters, cosmic filaments. Scientists have mapped these structures and have a good understanding of how large cosmic objects can get while still being physically coherent. There are limits. Gravity can only hold so much together across so much distance. The Lyman-alpha blob discovered in 2006, nicknamed Himiko, is a massive glowing cloud of gas over 55,000 light-years across. It was found at a time in the universe's history when structures that size simply shouldn't have had enough time to form yet. The universe was too young. Matter hadn't had enough time to clump together into something that enormous. But there it was, already fully formed, already enormous, sitting in the early universe like it had always been there, completely unbothered by the fact that cosmological models said it shouldn't exist yet. Scientists are still arguing about how it formed so fast. The leading explanation involves multiple galaxies merging at incredible speed, but even that doesn't fully explain the scale. Himiko remains one of the most puzzling objects ever discovered, a cosmic structure that simply arrived too early to the party. At number 5, we have fast radio bursts, the universe's most unexplained signals. In 2007, scientists reviewing old telescope data found something strange. An incredibly powerful burst of radio waves that lasted less than 5 milliseconds, but released more energy than the sun produces in 3 days. They called it a fast radio burst and assumed it was probably a one-time event from some exotic cosmic phenomenon. Then they found more, hundreds more, coming from all directions. Some of them repeat, some pulse in regular patterns. One of them appears to repeat every 157 days like clockwork. We've traced some to distant galaxies billions of light-years away. We still have no consensus on what causes them. The leading theories involve magnetars, colliding neutron stars, and exotic stellar objects. But here's the thing. None of these explanations perfectly fit all the fast radio bursts we've observed. Some behave in ways the proposed sources can't explain. Some repeat in patterns that suggest something almost deliberate. We detect roughly 800 of them per day across the sky, every single day, and we still don't know what's making them. They arrived in our data without explanation, they continue without explanation, and every new observation raises more questions than it answers. Number 4 is the axis of evil, and yes, that's its real name. The cosmic microwave background is the leftover radiation from the Big Bang. It fills the entire universe and should be almost perfectly uniform in every direction. Any slight variations should be random, scattered, with no preferred orientation. That's what all our models predict. That's what basic cosmology demands. But when we mapped it, we found something deeply unsettling. The variations in the cosmic microwave background are not random. They align. There's a preferred direction running through the universe, a pattern that shouldn't be there. Cosmologists named it the axis of evil because it directly challenges the foundation of modern cosmology, the idea that the universe looks the same in all directions. This alignment is so unlikely to happen by chance that scientists have spent years trying to explain it away as instrument error or data processing artifacts. But multiple independent measurements keep finding the same thing. The universe has a direction. It has an orientation, and nobody can explain why. The axis of evil quietly dismantles assumptions so fundamental to physics that admitting it's real forces scientists to reconsider everything from the Big Bang itself to the basic structure of space. At number 3, we have dark energy, the force that shouldn't be accelerating anything. Here's something that seems obvious. If you throw a ball up, gravity slows it down and brings it back. Makes sense, right? Now imagine throwing that ball up and watching it go faster and faster the higher it gets, defying gravity entirely. That's essentially what the universe is doing. The universe is expanding. We've known that since the 1920s, but in 1998, scientists discovered it's not just expanding, it's accelerating. Every galaxy is flying away from every other galaxy, and they're doing it faster and faster over time. There is no known force that should be causing this. Gravity should be slowing the expansion down, not speeding it up. So scientists invented a term for whatever is causing it: dark energy, and it makes up approximately 68% of the total energy content of the entire universe. Think about that. 68% of everything that exists is something we don't understand, can't detect, can't measure directly, and cannot explain from first principles. We gave it a name, stuck it into our equations to make the math work, and called it a day. Dark energy is essentially a placeholder for our ignorance dressed up in scientific language. The universe is mostly made of something that has no business doing what it's doing. At number 2, we have the black hole that's too big for its galaxy. There's a relationship between galaxies and the supermassive black holes at their centers. The mass of the black hole is typically about 0.1% of the mass of the galactic bulge surrounding it. This ratio is consistent across thousands of galaxies. It's one of the most reliable patterns in all of astrophysics. Then there's NGC 1277. This galaxy is relatively small, unremarkable in most ways. But at its center sits a black hole 17 billion times the mass of our Sun. That's not 0.1% of the galaxy's mass. That's 59%. The black hole is so disproportionately massive that it barely leaves room for the rest of the galaxy to exist. By every model we have, a black hole that size should have either consumed the entire galaxy or disrupted it so violently that the galaxy couldn't have survived. But NGC 1277 is sitting there, galaxy intact, hosting a black hole that dwarfs everything around it in a way that breaks the fundamental relationship between black holes and their galaxies. It's like finding a dog the size of a house living in a normal apartment, somehow perfectly fine. And finally, at number 1, we have the Hubble Tension, the crisis that's tearing cosmology apart. Scientists have 2 completely independent methods of measuring how fast the universe is expanding, a number called the Hubble constant. One method looks at the early universe using the cosmic microwave background. The other looks at the current universe using supernovas and variable stars. Both methods are incredibly precise. Both methods have been checked, rechecked, and verified by multiple independent teams across decades of research. And they get different answers. Not slightly different. Different enough that they can't both be right. The gap between the 2 measurements is too large to be explained by instrument error or calculation mistakes. Something is fundamentally wrong, either with our understanding of the early universe, our understanding of the current universe, or, most disturbingly, with the laws of physics themselves. Cosmologists call this the Hubble Tension, and it has the entire field in crisis mode right now. Some are proposing new forms of dark energy. Others suggest there are unknown particles from the early universe affecting the calculations. A few are even questioning whether the speed of light has always been constant. We built the entire framework of modern cosmology on assumptions that the Hubble tension is now quietly undermining. Everything we think we know about the age of the universe, its size, its fate, all of it rests on resolving a contradiction we don't know how to fix. Space doesn't just break the rules occasionally, it breaks them systematically, repeatedly, and at the most fundamental levels. Every time we think we've figured something out, the universe reveals another exception, another anomaly, another thing that simply should not exist but does anyway. And honestly, that's what makes it incredible. Every broken rule is a door. Every impossible object is an invitation. Every anomaly is the universe reminding us that we've barely scratched the surface of understanding where we actually live. If this blew your mind even a little, hit that subscribe button and turn on notifications so you never miss an upload. We've got plenty more of these coming.